Have you ever stopped to think about the world around you? Not just the big things like the sun that warms your face or the earth beneath your feet. I mean the truly enormous and the incredibly tiny. For the last century, our understanding of the universe has rested on two monumental ideas. These are the twin pillars of modern physics. On one side, we have Albert Einstein's theory of general relativity. It's the best description we have for gravity. It explains why planets orbit the sun and why you don't float off into space. It's a theory for the big, the massive, and the cosmic ballet of stars and galaxies. It's beautiful, elegant, and has passed every test we've thrown at it. On the other side, we have quantum mechanics. This is the rule book for the other end of the scale. It governs the world of the very, very small. Think of the atoms that make up your body and the even smaller particles inside them, like electrons and quarks. So what happens when the irresistible force meets the immovable object? What happens when you need both theories at the same time? This is the central mystery, the biggest puzzle in all of physics today. Think about the very beginning of the universe, the Big Bang. Or think about the heart of a black hole, a point called a singularity. In these extreme environments, you have gravity that is immensely powerful, but it's acting on the scale of quantum particles. Here's the catch. When you try to put the equations of these two theories together, they just don't work. The results they spit out are nonsensical infinities, which is a sure sign for a physicist that something is fundamentally wrong. Let's start with something familiar. Gravity. The story goes that Newton saw an apple fall from a tree, and it got him thinking. He wondered if the same force that pulled the apple to the ground was also the force that kept the moon from flying off into space. Newton's big idea was that gravity is a universal force. Every object in the universe with mass pulls on every other object. Enter Albert Einstein. At the start of the 20th century, he wasn't satisfied with Newton's picture of gravity as an instantaneous, invisible force. Einstein's big idea was this. Gravity isn't a force in the traditional sense. It's a consequence of the shape of the universe itself. Think of placing a heavy bowling ball on a stretched-out rubber sheet. The ball creates a deep dip in the sheet. Now, if you roll a smaller marble near the bowling ball, it doesn't get pulled directly by the ball. Instead, it follows the curve in the rubber sheet created by the ball. The Earth isn't being pulled by the sun. It's simply following the straightest possible path through the curved space-time created by the sun's immense mass. In 1919, during a solar eclipse, an expedition led by Sir Arthur Eddington confirmed this prediction. Starlight was indeed being bent. Einstein became an overnight global celebrity. We're diving down the rabbit hole into the world of quantum mechanics. And I have to warn you, things are about to get seriously weird. Down here at the scale of atoms and the particles inside them, the familiar rules of our everyday world simply don't apply. One of the core ideas of quantum mechanics is that these particles aren't just particles, they are also waves. There is a classic experiment that demonstrates this quantum weirdness so perfectly that it's impossible to ignore. It's called the double-slit experiment. When you do this experiment with electrons, even firing them one by one, something completely different and utterly astonishing happens. You don't get two bands. Instead, you get a whole series of bands across the screen, an interference pattern. This pattern proves that the single electron must have behaved like a wave and gone through both slits at the same time. Now, for the truly bizarre part. The moment you try to find out which slit the electron actually went through, by placing a little detector at one of the slits, the interference pattern vanishes. As soon as you look, the electron stops acting like a spread-out wave and behaves like a well-behaved particle. It's as if the universe knows it's being watched. But in 1975, a team of scientists managed to pull it off in a landmark experiment that was both simple and profound. The experiment used a neutron interferometer, which worked by splitting the wave function of each neutron into two separate paths. One path traveled horizontally, while the other was directed to travel slightly higher before being brought back down to recombine with the first path. This subtle difference in their ticking rate was the key. This is where atomic clocks come into the picture. These are the most accurate timekeeping devices ever created by humanity. In 2010, a team at the National Institute of Standards and Technology used two ultra-precise atomic clocks and placed one just 33 centimeters higher than the other. After running the experiment, they found that the higher clock was indeed running slightly faster than the lower clock, exactly in line with Einstein's predictions. The idea is to take a massive object, massive by quantum standards at least, and put it into a spatial superposition. If gravity is quantum, it would become entangled with the superposition, creating a measurable quantum link between the two masses. This is an immense technical challenge. The slightest vibration, stray photon, or air molecule could observe the particle, causing its superposition to collapse. Black holes are not just cosmic vacuum cleaners. They are the most extreme environments in the universe, making them perfect natural laboratories for testing our ideas about quantum gravity. In the 1970s, Hawking showed that black holes are not completely black. Due to quantum effects near their event horizon, they should slowly radiate energy. Here's the paradox. Quantum mechanics has a strict rule that information can never be destroyed. But Hawking's calculation suggested that the radiation coming out contains none of the information that went in. The most spectacular breakthrough in gravitational physics in the last century was the first direct detection of gravitational waves in 2015. Scientists were able to measure the tiny ripples in the fabric of space-time caused by the collision of two massive black holes over 1 billion light-years away. A true theory of quantum gravity would predict that these waves should be made of individual quantum particles of gravity, which theorists have named gravitons. All the stars, planets, and galaxies we can see only make up about 5% of the total energy and matter in the cosmos. The other 95% is a complete mystery. About 27% is thought to be dark matter, an invisible substance whose gravity holds galaxies together. The remaining 68% is dark energy, a mysterious force that seems to be causing the expansion of the universe to accelerate. We have no idea what these things are. Theorists are pursuing bold new frameworks like string theory, which posits that all particles are just different vibrations of tiny fundamental strings, and loop quantum gravity, which suggests that spacetime itself is woven from a network of indivisible loops. These theories offer tantalizing glimpses of what a unified reality might look like, a reality where spacetime is not fundamental, but an emergent property of something even more basic. Our exploration has led us to the very edge of what we know, and has forced us to stare into the vast abyss of what we do not. Is reality continuous or discrete? What happens to information that falls into a black hole? Are there other dimensions beyond the ones we experience? Ultimately, the search for quantum gravity is the search for a theory of everything, a single, elegant mathematical framework that can describe all the fundamental forces and particles of nature. You might be wondering, what does any of this have to do with my life? The drive to understand this connection is about something much more fundamental. It's about our place in the universe. We are a species driven by curiosity. We want to know the rules of the game. The search for quantum gravity is the search for that single, unified story. The next time you feel the solid ground beneath your feet, remember that you are standing on a planet held in orbit by the gentle curvature of a dynamic space-time, and that you yourself are made of quantum particles living in a world of probability and chance. The quest to unite those two truths is the quest to understand, quite simply, everything.